Welcome to the Picture Language Seminar. It's a very nice day here in Cambridge, and we're happy to have John Imbrie. But next week, I look forward to the talk by Emily Rial, and the week after by John Wei Pan. And because of the time difference, we've agreed that Pan's talk will start half an hour earlier at 9:30. So I just wanted to warn you about that. John Imbrie is an expert, having worked on quantum field theory, statistical physics, phase transitions, and properties of random walks, and established beautiful things in all of these subjects. Today, he's going to talk about many-body localization near the critical point. So John, we're looking forward very much to your talk.
Okay, well, I'm very happy to be able to talk about this work, and which I'm very excited about. And maybe I should share my screen. So what we're talking about is many-body localization near the critical point. And it's important to note that there's sort of a mixture of different levels of rigor in this talk. And as I begin to introduce the notion of many-body localization and some work from 2016 that I did, well, that's a mathematical result. But then the more recent work that really is the main focus of this talk is published in the Physics Journal, Physical Review. And so there's tons of approximations and whatnot, but still it's a very interesting set of ideas. And in the spirit of mathematical physics, I mean, I'm doing controlled approximations as best I can and as best we can. But it's something that, at least at the moment, we need to do in order to get to an understanding of the critical behavior. And actually, there's some interesting mathematical questions about some of the models that I'll introduce along the way. It could be amenable to more rigorous study. So well, here's the abstract, which maybe I'll skip over. Here's the outline of the talk. To begin with, I don't want to assume that everyone knows what MBL or many-body localization is, so I'm going to devote, I don't know, 15 minutes or so to an outline of some of the main features of MBL, and then I'm going to proceed to mention some of the insights from my, I guess I call it a partial proof of MBL from 2016, primarily focused on the notion of percolation of resonant regions. And to the extent that that informs the picture for the transition, that's very useful to review that. So then we're going to go to a simplified picture, so-called strong disorder renormalization group, where you take the line, which is initially, we're thinking about a spin chain, but we just simplify the picture to just a sequence of alternating thermalized and localized intervals, and understand what happens to that picture as you flow the renormalization group. And then we can begin to discuss the transition out of the MBL phase in terms of especially this avalanche-driven transition, which we'll get into in the latter part of the talk. And then we'll be able to compare the resulting equations with a very similar situation from Kosterlitz-Thouless, RG. All right, so let me begin then with talking about the phenomenology of many-body localization. So what are we talking about? We're having a many-body quantum system like a spin chain with disorder, so quenched disorder. here are some features that we may observe, which I would like to think of as the essential features of an MBL system. Firstly, you have absence of transport, very much like what you have in an Anderson localized problem, except that's really just a single particle problem, whereas now we're talking about a many-body system. But you can think of MBL as kind of Anderson localization in configuration space, that is the configuration of all those spins. And you can measure it, for example, with IPR measures. In terms of entanglement, you have area law rather than volume law. There's this violation of ETH, which is not the Swiss university, but rather the eigenstate thermalization hypothesis, which is basically a conjecture having to do with the idea that individual eigenstates are representative of a whole thermal ensemble. It's basically a measure of the extent to which a many-body system is thermalizing. In terms of level statistics, the eigenvalues of the Hamiltonian, you have absence of level repulsion, just as you would in an Anderson localized problem. And you have logarithmic growth of entanglement in time for an initial product state. So as I said, a typical example of an MBL system would be this one, this disordered spin chain. This particular one, built from the Pauli matrices, is the one that I actually used in my 2016 paper. And one thing that's worth noting is the extent to which this particular Hamiltonian is very close to a diagonal Hamiltonian. We have the Pauli Z matrices are diagonal in this in the standard basis. So we have the first and third term based entirely on the Z components. So those terms are diagonal. The only off diagonal piece is the middle term here. And so if we go to weak coupling, these gammas are small. And you might think that one can do a perturbation theory in the off diagonal terms, and that's exactly the way things work. And you try to show that the eigenstates, if you cover up this middle term, the eigenstates, of course, are just tensor products of 0, 1 and 1, 0. And if you turn on this term weakly, you might hope that the eigenstates of the Hamiltonian still resemble that in an appropriate sense. The way that this has been discussed in recent years has been in terms of so-called local integrals of motion, or LIMs. So we say that a fully MBL system has a complete set of conserved quantities, quasi-local in nature. If you have, but we say that these complete set of conserved quantities is a key feature of a fully MBL system. How do we know if we have a complete set of quasi-local locals integrals of motion, and can we construct them? Well, the way to construct them is to find a quasi-local unitary that diagonalizes the Hamiltonian. So here we can say that this unitary U diagonalized the Hamiltonian. What do we mean by quasi-locality then? It means that basically that if you have U is operating on a set of spins in a non-trivial fashion that span a distance L in the lattice, then it should be very close to the identity up to exponentially small terms in L. And of course, this isn't, in a system involving quenched disorder, there's always going to be rare regions where whatever property you're looking for is going to fail, or the Griffiths regions or resonant regions. So we don't insist that this U be close to identity everywhere, but it should be close to identity everywhere except for a very rare set of regions. So once you have this way of diagonalizing the Hamiltonian, you can define local integrals of motion by applying the reverse rotation on the spin variables. And then these tau variables are actually the local intervals of motion. You can just easily check that if you take the commutator with H, it's the same as the commutator of the diagonal matrix we defined above, which of course then is 0. So it's clear you have all these conserved quantities. The system is very different. It's really not exploring the complete configuration space. Let's say if you run the time evolution, kind of similar to the Anderson localization situation where you have a particle sitting close to the origin, and you run time and it remains close to the origin. It's not exploring all the sites it could possibly visit. And indeed, those properties that I mentioned before, these all follow from this notion of Lyams. All right, so now let me just get down to a very simple example, which will be illustrative, not just of MBL, but also of some of the arguments that I'm going to be giving later on. Just take a single spin. So then this matrix has the diagonal elements H and the off-diagonal elements gamma. And if you can see there are very, very clearly two regimes. If the off-diagonal term is much smaller than the level spacing, the eigenfunctions, once again, are going to be close to the basis vectors. And in fact, you can use the basis vectors, you know, they can be deformed continuously into the basis vectors, so that can be used as a labeling system. At the other extreme, if the off-diagonal terms are dominant, then the eigenfunctions are going to be close to these spread out eigenfunctions, if you will, 1, 1, and 1 minus 1. So we call this hybridization. And there's no longer any meaningful way to associate the eigenfunctions with basis vectors. So MBL is, in essence, kind of a this picture, but reproduced in this large Hilbert space where we take a tensor product of this 2x2 matrix over all the sites in the system. And when we have MBL, we can basically identify individual eigenfunctions with tensor products of the basis vectors 0, 1, or 1, 0. Okay, so now we get into the question of how do you actually build these Lyams? How do you build these quasi-local integrals, quasi-local unitaries? Well, you can do it perturbatively, but you know, that doesn't necessarily answer the question of whether non-perturbative effects are going to spoil this picture that you see. Indeed, if you go to higher dimensions, it's believed that non-perturbative effects are going to destroy many-body localization. So anyway, it's so important to consider the effect of non-perturbative effects. I gave a non-perturbative proof of MBL in 2016 for a one-dimensional spin chain. Although this proof depends on a physically reasonable assumption on eigenvalue statistics, essentially that the level spacings in a system of n spins are no smaller than some exponential in n. So in effect, you know, the numerical evidence of MBL is of the MBL transition is not all that strong. The systems that can be analyzed are not that large, and some are even questioning that evidence. So yeah, it's very useful to have this non-perturbative proof out there.
John, is the numerical evidence all in one dimension?
Well, that's I mean, it's an entirely separate question as to what happens in higher dimensions. So as far as this slide is concerned, I'm talking about one dimension. There is some work in higher dimensions, but you know, you can get you can't get to very big systems in higher dimensions. So let me just mention the percolation picture. Although this picture is a two-dimensional picture, but I just happen to have it handy. The whole idea is to control the probability of resonances and show that resonances don't percolate in the one-dimensional lattice. Okay, so now let me get in. I'm now in this sort of transition region of the talk where I'm trying to make a bridge between the discussion of the MBL proof and the more recent work that I did with David Huse in Morningstar on the behavior of the transition out of the MBL phase. So one of the key features of this proof was one of the key problems was how to deal with these resonant regions naturally. And basically, one needs to show that the resonant region can sort of decouple from its environment in much the same way as individual spins are decoupling from each other, at least for a weak coupling. But as it turns out, you can't just directly unlink a resonant region from its environment. There needs to be a buffer zone. And the reason for this is, well, you do have exponential decay in interactions. The interactions are given by some graph involving basically steps in the lattice. And if the graph traverses the distance L, then it's going to be basically of order L in perturbation theory, and so it's going to be of order gamma to the L, where gamma is a small parameter describing the strength of the interaction. But it's important that this strength gamma to the L be smaller than the typical level spacing in the resonant region here, which is 2 to the minus R. And so it should be clear then that you need to include this buffer zone of size roughly of order R. And let's say if it was exactly equal to R, then it would be 2 to the minus 3R. And then for gamma sufficiently small, gamma to the L will be smaller than 2 to the minus 3R. Okay, well, this is all well and good for the case I was dealing with back then, where gamma was just taken to be a sufficiently small parameter. But now if we want to go toward the transition, this phenomenon is going to become problematic because gamma is going to get less and less small, and I guess in an extreme case it could get to be bigger than 1/2, and then there would be no way of decoupling this resonant region from the rest of the chain. So basically, this whole buffer zone ends up, we expect it to be thermalized by this resonant region. And also it's worth mentioning that this is a key distinction between one dimension and higher dimensions. Since in 1D, the buffer zone is volume comparable to the volume of the block. But in higher dimension, of course, you have, it can be much larger. And so this leads to problems in trying to extend these ideas into higher dimensions. And in fact, most people would say you don't have true MBL in higher dimensions. You may have a sort of quasi-MBL where things remain localized for very long time scales, but if you go to infinite times, you do have thermalization. All right, so now I want to talk about, well, the renormalization group picture, which underlies the proof, the 2016 proof. So in RG terms, what we're doing is we're performing these rotations involving terms in the Hamiltonian up to order gamma to the L. This can be thought of as analogous to integrating out short distance degrees of freedom in more familiar realm of traditional RG. Because what happens is then that the Hamiltonian itself undergoes, we integrate after these rotations, the terms in the remaining terms of the Hamiltonian end up flowing. They get smaller and smaller under this RG. At the same time, we need to deal with these resonant regions. So up to some size R, they're eliminated. Once the RG's length scale is large enough so that the remaining interaction terms are smaller than the level spacing in the region. Now, important to note that including the buffer zone with total size R plus 2L. So at that point, if the interaction terms are sufficiently small, then the region host, you might think of it as a metaspin, which takes 2 to the R plus 2L values. But okay, so it's a very complicated spin, but if the interactions are sufficiently small, there's still going to be very little hybridization with spins elsewhere. Now, if we go again deep into localized region, this RG has the property that the density of the remaining regions, including their buffer zones, goes to 0 with L. So that's kind of what you expect out of an RG that leads to an MBL phase. But it's important to note, which I've hinted already, is that there are two effects in play. Firstly, there's this notion of elimination of smaller isolated resonant regions that reduces their density. And secondly, there's an effect where the buffer zones end up getting fattened up. As the length scale increases, so does do these neighborhoods, buffer zones, fatten up. And so these two effects are fighting one another, but I was able to show that number one, it dominates number two deep in the weak coupling or strong disorder region. And ultimately the density goes to 0 as L goes to infinity. All right, now let's talk about moving toward the transition. And we need to think about this avalanche effect, which has something to do with what happens when this decay rate, gamma to the L, reaches, gets poorer and poorer, and eventually reaches some critical value. So for weak disorder, decay rate for weaker disorder, the decay rate can be reduced to the point where there's no size for the buffer zone that can insulate the region from the rest of the chain. And this is the avalanche instability. If you want to talk about this quantitatively, you can estimate the size of matrix elements connecting the resonant region with spins outside the buffer zone. And well, this is gamma to the L, as I mentioned, and then there's a sort of the kinematic factor which comes into play, having to basically the square root of the number of states in the Hilbert space for the region with the buffer zone. This has to be small compared with the level spacing, which is 2 to the minus the volume of this buffered region. And for this to work out, for the perturbation theory to work out, we need then gamma to the L smaller than 2 to the minus R plus 2L over 2. Really, this is the same perturbation theory that I mentioned way back at the beginning when I was talking about a single spin. You remember I said if the off-diagonal matrix elements are smaller than the diagonal ones, then the eigenstates resemble the basis vectors. It's really the same thing going on here. All right, so if we look at this inequality here and just solve it, we see that this the length L, basically the width of the buffer zone, has to be at least this size. It's proportional to R, but there's a denominator here, which of course, as anticipated, the denominator goes to 0 as gamma increases to 1/2. So there's something special about the decay rate with decay factor 1/2, which makes it impossible to decouple these resonant regions from the rest of the lattice. And this is basically the avalanche effect, which was pointed out by Deroque and his collaborators back in 2018. It seems like a long time ago now, but it was actually very controversial when he introduced the idea. I think most people have come around to it, but there were lots of yelling and screaming in physics talks about whether some of Deroque's ideas were valid or not. Okay, so we'd like to understand the implications of this avalanche effect for the RG. And so here I'm going to have to go.
John, can I ask a quick question here?
Sure.
So are you identifying gamma equals, I don't know, 1/2 or whatever as the critical parameter, or actually, or it's an approximate statement? Of course, I would expect.
Well, yeah, I mean, I've somewhat conflated gamma, which I actually put as a number in the Hamiltonian, but at this point, I'm really thinking of gamma as the actual rate of decay of matrix elements.
Oh, so those are, yeah. So you're really, those are two distinct things.
Yeah, right. So I've left that behind. I'm talking now really in terms of some kind of an effective parameter representing.
Okay, so the gamma is an effective gamma.
Yeah, right.
Describe some decay rate.
Yeah, it would be like if you have really, it's kind of a mass or log mass.
Okay.
Mass, but
yeah.
Now we're talking about
that
the
helps.
actual physical mass rather than the bare mass.
Yeah. All right. Thanks.
But John, modulo that assumption, is this a mathematical statement or is this a physics approximation?
Well, if we go to no, I mean, this is a physics paper, PRL. So, it's supported by numerical evidence and, and lots of theoretical discussion about it, but there's no mathematical results supporting it. Yeah, and just to reiterate, I'm transitioning over to the physics world, right? I mean, this paper that I'm discussing with Morningstar and Huse, this is a paper in Physical Review. We make lots of approximations, and I would say they're controlled approximations, but it's definitely not a rigorous result. I mean, similar in spirit to Kosterlitz-Thouless when they came up with their theory of the transition. It was not a rigorous result either.
But Jürgen Tom made a theory about that.
Yes, and actually a lot of those ideas are, they've always been very influential to my work, but in particular, this notion of percolation of resonances and erasure and pairing up, as we'll see in the simplified RG, is actually, very similar to the ideas that go back to their work on KT. So, so here we're going to go to a simplified RG, and what we do is we take a system which initially is just a spin chain, but we're going to identify those regions that are localized. We call them L blocks, and thermalized, we call them T blocks. And the idea is that, well, if you were actually to run a time evolution, thermalization is something that is a process which takes place gradually. certain regions which are have weaker disorder than others will tend to thermalize first, and it's really the interaction between these regions, and as I discussed a moment ago with the avalanche considerations, which lead to an answer to the question of whether these localized regions take over the whole lattice or whether they remain as isolated blocks. So anyway, we have an RG, so we have a cutoff lambda. The line consists of alternating localized intervals called L blocks and thermalized intervals T blocks. And we're going to assume the decay rate deficit X is constant in space. And here I didn't really define X but earlier, but basically this denominator here, which I said is going to go to 0 when gamma goes to 1/2, this is X. All right, so when X goes to 0, that means this decay rate is going to 1/2, and this length, the buffer size, is going to infinity. So actually, X is going to be one of the two key RG parameters of the problem. The other one was related to the density. So now we're going to assume this X is constant in space, and that's an approximation, but we can return to that later, but it can be justified once we understand the correlation length divergence using Chase-Harris arguments. All right, so
John, let's get back to that gamma again. So that in the Kosterlitz-Thouless picture, that would be like the usual 8 pi, right? Something like that.
exactly, yeah. So then X would be the difference between the temperature and 8 pi.
Yeah.
So actually, I think what I'm going to do here is I'm going to switch to my handy dandy Blackboard because I don't want to just talk about this, but I want to show it as well. Here it is. So this is the same slide here, and I'm just going to try to draw some picture here where we have maybe we have these dark lines are going to indicate the T blocks, the thermalized blocks are non-perturbative regions, and so we may have something like this. Maybe at some length scale. Remember, all of these T blocks have minimum length lambda. That's the RG cutoff. Then as we increment, lambda goes to lambda plus d lambda. These T blocks end up getting erased or absorbed into the neighboring L blocks if they're isolated. In other words, they're separated by more than a buffer size lambda over X from other T blocks. This lambda over X, again, this comes from the fact that X is in the denominator. That's the size of the buffer zone. So in this picture, you would say, well, let's say we're going down this direction. Lambda is increasing. And as we increment lambda, these guys are isolated, so they are going to disappear. But the buffer zone is going to end up connecting these fellows. And so this is what it will look like. And then we continue to increase lambda. Lambda gets to be this size. Eventually, it gets to the point where these two blocks are within lambda over X. And so then these end up getting joined up. And maybe this fellow gets disappeared because he's far enough from his neighbors. And so we continue along in this fashion. Once again, we can see these two effects in play. There's the disappearance, which tends to reduce the density, and then there's the grouping together coming from these this lambda over X buffer radius. which tends to increase the density. And the key question is which effect predominates. And by the way, I want to show, now if we imagine that, what is the effect of these disappeared guys? They don't fully disappear from the problem, but if we do it talking about the decay rate here, we're talking about the decay now. What happens is these, we still have the ghost of these disappeared resonant regions. There's no decay where they used to be. So we have interrupted decay. Basically, it's kind of like a short circuit, an electrical circuit. If you connect two nodes, then there's no resistance there. So you can see then that if you were to measure the decay in terms of overall distance, because of the interruption, the rate of decay is going to get smaller and smaller, the more of these guys that get erased. So all these effects are things that I had to deal with in the 2016 proof, but they were manageable because in the end of the day, there was no real change in the decay rate up to some overall factor. But now we're studying this situation where we're getting close to the transition, and this interruption in decay is actually one of the key features of the problem. So anyway, this is basically what I'm saying here about the avalanche parameter X flowing downward with the RG, because erased T blocks interrupt the decay of interaction. Okay, so let me go back to my original slides. So now I need to introduce the functional RG, which is basically a mathematical expression of what I drew in pictures in the previous slide. So what we have here is quenched randomness, or ID randomness. So we can assume that these T blocks appear at random, meaning that they have an exponential distribution in space. In other words, for each subsequent T block outside of the minimum distance that's determined by the RG rules, is going to appear with an exponential distribution. And so this RU to the minus R is the probability that the length of an L block lies in this range, lambda over x plus W, lambda over x plus W plus TW. So if we just have an exponential distribution, that means this R is the rate. That's one of the key parameters, but it's a little more complicated than that, because once you end an L block, you have a T block. That T block can have an arbitrary length with minimum lambda. So really we have separate rates for each length. We integrate over the lengths from lambda to infinity of some R lambda of L. So that's why it's a functional RG, because this R lambda of L is really a function that's describing the flow with lambda. And I put in this slide here showing the actual equations. Not that I want to really go through it, but just to show you, this is a serious mathematical model, which in principle can be analyzed directly. We were not able to solve it directly, but we were able to understand the behavior of this flow using controlled approximations. Essentially, you have a convolution here, which coming from the fact that larger T blocks come from pairing up of smaller T blocks. And then we have this flow of X coming from this decay rate. This can be quantified as well. So anyway, to get to the notion of the critical behavior, we need to make a further reduction from the functional normalization group to the two relevant parameters in the problem. We already know that one of the parameters is going to be this parameter x, this deficit decay rate. We want to have the other one relate to the density, so we take the this rate r lambda of lambda, which has dimensions 1 over length squared, because you know, r of course is a rate, so that's dimensions 1 over length. There's another integration here, so little r has dimensions 1 over r squared. And so if we just pull out that dimensional factor, we get the other RG parameter y. So again, so this is related to the density. And we certainly anticipate that just like in KT, when y is 0, x bigger than or equal to 0 will be the fixed line of the RG. Because there you have really the vanishing density, y equals 0 for the T blocks. The diagonal transition will be governed by the point at x equals y equals 0, where the fixed line becomes unstable. All right, so now we get into trying to get an approximate understanding of the RG in terms of these parameters x and y. The key thing to recognize is that the dominant mode of production of T blocks of size lambda over x should be the combination of component T blocks of size close to lambda. Here, let me do the same thing and go to the blackboard, if you will. So here we have, remember we had this combination of T blocks like this. If we think about it, if you're going to form a T block, a large one, the most efficient way, or like the most probable way of doing so, is to have relatively small component pieces joined together to form this large block. Because after all, there's rapid decay. If this guy was much larger, it would just be that much less probable. And in fact, if you think about it, we can sort of integrate over all possible ways of forming this block of this size. It involves an integration over all the lengths here and all the lengths here. So that means we're effectively going to get a factor of r for that and a factor of r for that, which combine to this density r lambda of lambda over x. So anyway, this is this equation here, which is basically saying that the describing all the ways you can get a block of this size by combining subblocks. And this can be obtained also by going back to the FRG equation that I flashed for you earlier. We also want to note that this r lambda of L is going to depend weakly on lambda between XL and L. Again, that's because the dominant mode of production is going to involve the smallest possible component blocks, in this case of size about XL. So this means that essentially you have dimensional form for the behavior. This r lambda of L, which I said was dimensions 1 over length squared, actually behaves like YL over L squared for L in this range. And it also R is dimensionally going to be lambda, R lambda. So what this means, we can take this key equation here and express it in dimension-free terms, Y, by plugging in these relations, especially this one here. So anyway, in dimension-free terms, we have this key relationship that Y at this longer length scale, lambda over X, is equal to Y over X squared. So, and it's amazing what you can do with this equation. In fact, that's the key to the whole analysis. So let me just summarize then. We're approximating. Oh, by the way, let me just go back to this once again. So this is r squared, right? So so that's, it might make sense that there's a squaring operation in the RG. So if we go to a flow, we typically use log lambda to parameterize the RG. And then we have really a combination recursion flow. dx dt is minus y, so the decay rate decreases according to y. And then we have this recursion relation, y lambda over x is y over x squared. Now, if you think about this key recursion relation on the right, if supposing y is on the curve x squared, for example, then y over x will be x, and then we square that, we get back to the curve y is x squared. And you can actually kind of ignore the flow of x as far as this consideration is concerned. And that tells us that the separatrix, if you will, of this flow is going to be the curve y equals x squared. And in fact, if you start on the curve y equals x to the 2 plus delta, a little bit below the separatrix, or above, depending upon the sign of delta, and you plug it into this relationship, you end up on the curve y equals x to the 2 plus 2 delta. So there's, again, we see that the separatrix is asymptotic to this curve. We also see the, if you will, this exponential departure from the separatrix once you're off of it. But it's interesting to note that somehow you really need to take a logarithm here to see kind of a linear form for this RG. Once you know that this is the separatrix, then you can plug that in. We have dx dt equals minus x squared. And so that means the behavior of x and y are determined. There, x goes like t inverse, y goes like t to the minus 2. And so, okay, we can proceed to analyze the behavior of the diverging length. And I don't think I want to go through the details of the analysis, but at this point, it is just an analysis of what is essentially a 2-parameter flow, although it's defined in terms of a recursion instead of a flow. We can define a diverging length in the usual fashion. Really, it's the length scale at which an orbit departs the vicinity of the separatrix from an initial small displacement delta 0. And so, yeah, if you analyze this flow, we see that this length is given by this interesting looking formula here, delta 0 to the minus log delta 0 inverse. So now as delta 0 goes to 0, as we go into the critical point, critical temperature or critical disorder, this clearly diverges faster than any power of delta 0. So we have in effect nu equals infinity. Nu being, under normal circumstances, nu would be this exponent here if it were a constant. And this may be distinguished from the Kosterlitz-Thouless form, which also involves nu equals infinity, but it has a very different divergence, e to the delta 0 to the minus 1/2. So this it's worth pointing out that this flow that we've come up with has a lot of resemblance to the KT flow, but there's in the KT flow, there's logarithmic slowdown along the separatrix. As we saw, this, x is t inverse, y is t to the minus 2, t is log lambda, so that's this logarithmic slowdown along the separatrix. And of course, nu equals infinity, but in the KT case, the progress is also slow going orthogonal to the separatrix. In our case, we have what is very nearly exponential divergence away from this separatrix. It does proceed through this logarithmically slowed RG time. Because you see we have y lambda over x, right? So that means each RG step, instead of going with a fixed factor of 2 or whatever, each RG step gets longer and longer in length space. And in the t variables, it's log x as the jump in length scales that proceed with each step. And this exponential divergence away from the separatrix, as I mentioned earlier, is something you see directly from this recursion. This delta goes to 2 delta. Anyway, so that accounts for the differences in the form of the divergence. And if you were to plot this, well, actually, you know, I've been working with the with this recursion slash flow, but you can define an equivalent flow equation for y, which mimics the behavior of the recursion. And here it is, it's dy dt is minus log 2 y delta. So you notice that really what this is, it's an equation for d by t of log y, right? In terms of delta. So it's basically kind of a representing the fact that you, and to some extent, the y equation, to make sense as a linear RG equation, you need to take a logarithm. When we write it directly in terms of y, then we have all these logarithms appearing on the right-hand side, which were actually sort of missed in earlier discussions of what would be the likely form for the flow equation for the MBL transition. So anyway, this is the flow equation for y, and we stick with the previously derived equation for x. This is what it looks like in the xy plane, although here I've plot square root of y instead of y just to make the details a little more clear. So there's a lot of interesting parallels with the KT picture. Maybe you've seen some of these already, but like the vortices in KT, that these T blocks represent non-perturbative effects. And the tendency of these effects to grow or shrink with the flow determines the phase reached from any starting point in the diagram. You can also think about the fact that vortex binding in traditional KT is really analogous to this T block erasure, as we've been discussing. Because when vortices bind, they kind of disappear from the problem. They just renormalize other parameters. And indeed, in KT, the vortices renormalize the stiffness when they bind. And in a similar fashion, when these T blocks are eliminated, they renormalize the decay rate. And as I mentioned, earlier works did suggest a KT picture for the transition, but they were assuming an analytic flow equation. And so they really missed the fact that this, because of this factor log y over log x minus 2, or which is really this delta parameter I've been working with, this puts this problem in a different universality class from KT. So anyway, I think that's a good place to stop, and happy to take any questions.
Well, thank you very much, John, for painting a beautiful picture of this transition. It would be nice to use this as a basis for mathematical proof.
Yeah, I think there's some, I think these models of alternating T blocks and L blocks are show a lot of interest. They're very straightforward to define probabilistically, and they have very interesting critical behavior, which would be worth studying. Just for them from their own point of view, even aside from their interest and relevance for the NBL transition.
So are there any questions or comments for the discussion?
Yeah.
Werner.
Okay.
Let me just ask, so go ahead.
Leslie, thank you. Then I have two questions, quite disconnected. One is, do you have an idea how the 3-point function would behave close to the transition?
Well, I'm not exactly sure which 3-point function you're talking about, but no, I haven't really considered to the extent that 3-body effects might have distinct critical behavior from 2-body effects. I haven't really considered that question.
The second question is just from your experience, so about the transition between mathematics and physics. Sometimes you have probabilistic ideas which are sort of convincing, but cannot be made mathematically precise. And sometimes the vocabulary which you the approximate vocabulary which you first which you first invent is exactly the formalism you need for an exact mathematical result. So probably, well, as Arthur already indicated, just the term T block, L block or so also would appear in an exact mathematical treatment. But what is your experience in similar situations?
Well, yeah, certainly the language, that picture was something that very much underlaid my proof in 2016 for of the NBL phase. So yeah, it was all very familiar to me. But you know, when you consider problems like what the next step would be, you don't want to bite too much off at one time, right? Otherwise, you'll just be beating your head against the wall. I mean, it's a problem. The actual critical behavior of NBL is a problem, you know, maybe decades into the future in terms of rigorous work. So again, I would just emphasize that these mathematical simplified versions have a lot of interest in themselves. You know, there's, for example, I'm not sure if there's any connection, but Derrida has been working with these probabilistic models, which he actually was able to prove rigorously that they have KT transition, and so it's quite possible that these models of alternating intervals could be analyzed rigorously, you know, with you know, in the near future, let's put it that way, rather than decades in the future.
Okay, thank you.
Tom, you had a question.
Yeah, I was going to ask about, so there was earlier work that suggested that there was a KT transition in one dimension, but they were actually, I mean, from what I understood you to say, they were actually getting the KT, you know, critical phenomena, whereas you're getting something different, right? Yeah.
And, you know, I guess this is maybe sort of been lost in the noise a bit, but in terms of how significant is the difference between the flow we found and the ones they gave. But, you know, of course, we consider, you know, they did a very reasonable thing. They just said, well, you know, let's just expand in powers of the disorder, right? Of the density. And so, of course, if you do that, you get KT. What we learned was that, no, you shouldn't be expanding in powers of disorder because there are these logs everywhere. And so if you think about these problems carefully, you get a different set of flow equations and a different universality class.
Yeah, so that's quite significant. I mean, can that be, I guess that's too hard to check numerically, or is it?
Yeah, unfortunately, well, I will say in terms of numerics, that there is actually sort of a rough agreement with what we have in the numerics, such as they are. Let me go back to the slides. So yeah, this behavior here with the log, if you you can basically think of the turn this around and say, what would be the effective nu that you would observe if you had a system of size lambda? And so, and it's basically log lambda. So, and then if you put in lambda is like, say, 1,000,000, then, you get log lambda is about 3. Very far from infinity, but actually that's similar to what people observed in some of the numerical experiments that have been done. It also indicates that you kind of have to go to the size of the universe if you want to get nu to be anything substantial.
Right. So is there agreement? Can you prove, I mean, numerically, can you check agreement with your functional equation and your effective flow?
Well, we have given fairly quantitative estimates on deriving the flow from the functional RG. I mean, we didn't do it rigorously, but it's a controlled approximations. It could be made rigorous in terms of that part of it.
Mm-hmm.
The functional RG itself, already, of course, has numerous approximations to get there, especially this notion of constant X. Which we had to make that assumption just to get the FRG as written. There's a more complicated FRG you can put down, which doesn't have that assumption, but that's, then you're just getting farther and farther from something that can be analyzed even approximately.
Right.
Is there any hope to go to higher dimension?
Well, yeah, of course, we don't believe that there's a transition higher dimensions. So, yeah, people are not suggesting the analogous models like these T block, L block models in higher dimensions. So it's rather an open question as to what the best way to study higher dimensions would be, but whether it be from an RG point of view or what.
So there are other comments from people who we can't see.
So is there some connection with Fisher's renormalization, Daniel Fisher's renormalization? I mean, I think I heard you and David mention something about that at some point.
Yeah, well, David always thinks that views this strong disorder RG as, yeah, that's basically a language going back to Fisher's paper. I'm not, well, you know, we've departed, you know, some distance from that idea, but, you know, the idea there was to, you look at the strongest bonds and integrate it out and so on and so forth. And that turned into something that could be handled analytically. So when we have this, you know, but there was no lambda there in that, as I recall. I mean, it wasn't really a length scale driven RG. It was, I guess it was an energy scale driven RG. This seems much more, when you're important here to use this length scale as a driver. But it's philosophically, they're very similar because the length scale and the energy scales are connected, at least approximately, because the energy differences are exponential in lambda, and then the time is exponential in the energy.
Okay, thanks. That's helpful. Yeah.
Okay.
Very nice talk. I enjoyed it.
All right.
So Paul, do you have a comment?
Well, just a very quick question. I mean, I thought the people who predicted this was KT were using at least some variation on the Fisher stuff. Is that right? Or am I remembering wrong?
Well, yeah, all these papers, and there were a lot of them, basically started from this so-called strong disorder RG, where this model of the alternating intervals, thermalized and localized intervals. And this got improved over a course of 4 or 5 papers in physical review. You know, initially there was no asymmetry between the L and the T blocks, and then that was recognized as being an important thing. And this infectiousness coming in this factor, you have lambda over X, this infectiousness, which itself diverges, is obviously a very key component to the KT picture. But ultimately, you know, what people got to the point was, yeah, okay, there are these two effects, and if one predominates, you're localized. If the other effect predominates, you thermalized. But then you just write down, you say, okay, well, let's just expand it in powers of Y. And once you do that, you say it's, well, you know, most RGs are, you know, involve power series, right? We're just used to that. But in this case, that's actually a bad idea because you miss those logarithms. The RG really does have a linear approximation, but only after you proceed to log Y instead of Y.
Sounds like an important distinction.
Yeah.
So conceivably, they could then, if now that this fact is known, or at least seems to be known, they could modify their procedure to do it that way and then get the same answer, or is that just something that's not going to happen in that sort of the usual approach, or is it to some extent that's what you've done? Basically, you've just figured out.
That's what we did. We did the analysis correctly. Well, that's how physics proceeds.
Okay.
People make successive approximations. Eventually it gets done right. And maybe we're biased, but we think we've done it right now.
No one's gonna say you're wrong. All right, good, thanks.
All right.
So are there any other comments? Well, if not, I'd like to thank you again, John, for a really beautiful picture, a wonderful talk, and we'll look forward to the next chapter.
Okay. I get right to work.
Yeah.
Well, thank you so much for the opportunity to present here, and I really enjoyed talking to you all today.
And we'll see you next week with Emily. Bye-bye. Bye-bye.